So for Lab 6, the Common Collector amp, we've given you a MultiSim file to get started. Um, we've just switched you over to online, so I figured that we should give you the MultiSim in case you haven't played with it, because now you're going to have to play with it. So this is a starter file. So you open up the file in MultiSim, and we've got the Common Collector amp in there with a couple of extra things. So to set the input, you double click on the function generator here, and you can set the input to different frequencies and amplitudes. So I'm starting off at 1 kilohertz and 1 volt peak. Now 1 volt peak is going to be 0.7 volts RMS. Okay, so that's how you would adjust the input. We've given you a multimeter here on the output, so plunk down a multimeter. These tools are all available here, and you can set the multimeter to read amps or volts and then AC or DC. So if you start the simulation, you can see that it's running here. It's putting in 1 volt peak, and I'm measuring on the output here 700 millivolts. This meter is an RMS meter, so it's telling you the RMS value. However, you can go up here and you can attach probes, and the probes can measure voltages at different points. I've put a probe down here, right here on the output, and I can see that there's, I can see the peak-to-peak voltage here, 2 volts. Makes sense because this is 1 volt peak, and I can see the RMS voltage at that point. That is both AC and DC. It doesn't look like it does AC voltage on its own. That's where this meter here comes in handy. So now you've got it running, you can put probes down, you got your meter. You can also look at the waveform, input and output of the waveform, make sure it's working correctly. I usually put the input on channel 1 up here, the output on channel 2, and then I can also look at, so there's the, verify that's working. You can also put a Bode plot analyzer down, and that tells you the frequency response of the circuit. If you drag this over, we get to this point here. So at 473 hertz, basically it's down a little bit. It's essentially 0 dB, and 0 dB is a gain of 1, which is what the Common Collector amplifier is supposed to have. So that's the correct value. You can kind of go over here, you go down to -3 dB. So I'm trying to dial in -3 dB here, and so that's at about 50 hertz. So that tells me the cutoff frequency of this whole circuit is about 50 hertz. Now when we calculate cutoff frequency, we do it one capacitor at a time. When I do his cutoff frequency, I assume he's a short. So you may find, and then when I do this one, I assume this one's a short. So you may find this is a little lower than the individual capacitors. That's because when you get the whole thing going, you're seeing the effect of all the capacitors. So if both of these had a 50 hertz cutoff, then the cutoff would actually be higher than that, lower than that. Okay, and then the last thing here, I put a switch in here for you. And what you can do with the switch is that you can hit the space bar, or you can just click on the switch. And what that does is it cuts the load in and out. And this is one of the ways that you can measure Z out. If I cut in a load, if I attach a load to this, I can see that there's a voltage drop that occurs. And what I can do is I can look at the no load voltage. I'm measuring it off of here. So the no load voltage of 702 millivolts. And then when I put 100 ohms on it, it drops down to 697.98 millivolts. It's only about a 4 millivolt drop, which means that the Z out is very low. But by knowing these values and by knowing the value of the load, you can figure out Z out. And you can figure it out using basically the rules you learned from DC. And you remember how to do those, right? Okay, I didn't think so. Let's take a look at how we're going to solve that. So over here, I've basically got the amplifier as a 2-port model. I've got the dependent source in the amplifier. I'm going to call that the no load voltage, because if this switch is open, then the voltage that appears here is this voltage. So you measure that. That was 702 millivolts. That's the no load voltage. We'll just write that down, and that we get that when the switch is open. And then when I close the switch, that would be the loaded voltage. That came out to 698 millivolts. So with these two voltages and the value of and the value of RL, we can figure out what Z out is. How do we go about that? Well, first thing I'd recognize is I've got a voltage divider here, and that the loaded voltage, the voltage across these two terminals, is basically this voltage times the voltage divider. So the loaded voltage is the no load times RL over RL plus Z out. Voltage divider. Okay, what do I do from there? Well, then you do like a bunch of algebra and you rearrange it so you get Z out on one side and all the other stuff on the other side. And then you put in your known values, then you solve for Z out. The other thing that we ask you to measure, so that's how you can figure out Z out. Looking at this, you can probably figure out gain off the oscilloscope. You can look at what's coming in, the peak values of what's coming in. You could also put down one of these meters on the input and measure the input voltage and the output voltage and then figure out the ratio. So that's how you can measure gain. You could put a resistor in here. You could break this open and put a resistor in here and measure the voltage before and the voltage after, and then use that to calculate Z in. So all of the things that we did in the previous labs, we can now do using MultiSim, and then you can record your results and submit them.